Welcome to Chemical Reactions, Chapter 8. Section 1 continues here, but this is Part 2 of the Section 1 presentation. Because balancing equations is somewhat of its own thing, as opposed to understanding the types of equations, a word equation with just the names of the substances and some symbols, a formula equation, which is simply all the formulas with their symbols, which would almost look, well, it looks exactly like a chemical equation, for the exception of if it's not balanced, we call it a formula equation, as opposed to a chemical equation, which is completely balanced, agrees with law of conservation of mass. Everything on the left-hand side of the arrow is the same as on the right-hand side of the arrow as far as how many atoms and what kind of atoms you have. So chemical equations and balancing. Okay, this section is specifically on balancing. There is a brief mention of energy and reactions towards the end, and also a little bit of information on what equations actually tell us once they are balanced, because they actually tell us more than just some numbers and substances. So there's a lot more to it than that. We'll just briefly go over that, but this is primarily about balancing. Okay, with balancing. Always when you have a formula equation, you should just check to see if it's balanced. If it's balanced, it obeys the law of conservation of mass, and if it doesn't balance, then either you can have a formula equation if that's just what you want, or you must balance it. And how we balance it are by using numbers we call coefficients, which are multipliers. And coefficients are numbers that are written regular size, just like the symbols would be, and they are written to the left of a substance. And so if I can activate my pen here, just as a, if I have H2O, if I were to write a 2 in front of it, that 2 would be a coefficient, and that 2 is a multiplier. So that would multiply my water by 2, so everything in water, I have double of it. But it would mean I would have 2 water molecules, not necessarily that, I'm talking 4 hydrogens and 2 oxygens independent of each other, because it's still a molecule. So anyway, we use coefficients to balance, and we do this when we need an actual chemical equation, because that's the name we use for a balanced equation. Whenever we have coefficients, we should always use the lowest possible coefficients that will balance the equation. So you may have an equation that balances with a coefficient of 2 and 1 and 1, but it would also balance with a 4 and 2 and 2, because it's the same ratio of numbers. And so we would always want to reduce the lowest terms if at all possible. Okay, so here's some tips. These would be worth writing down simply to guide you as you begin balancing. Now, sometimes balancing is a little bit of trial and error once you understand the system and what you're trying to do. But there are some things that will help speed you up, shorten the process, maybe make it more effective a little bit earlier, a little bit more success. So here they are. And I can activate the pen and check these things off because I got a little handy box there to do it. Okay, balance atoms one at a time. So sometimes I've had students and people, generally they'll look at NaCl, sodium chloride, and they'll try and balance the whole sodium chloride across the arrow, when you really should break it up and look at the sodiums first and then the chlorines, or vice versa. But look at atoms one at a time. Don't look at them as units. Now, you can get around that a little bit with polyatomic ions, and I'll show you that in a little bit. Balance atoms that appear only one time on either side of the arrow. Once in a while, you'll have oxygen that'll appear like in two separate compounds on the left or 2 separate compounds on the right. Other elements can do this, and those are a little bit more difficult to balance, especially at first. So I would balance other atoms first that only appear once on either side, and then oftentimes you'll find that by balancing those, other things that are mentioned more than once often balance just because of that. We can sometimes balance a polyatomic ion, PAI, as if as a unit. If it remains intact across the arrow. So let's say we have sodium nitrate on one side of the arrow, whatever we're adding it to, and then it reacts, and then it creates maybe a calcium nitrate on the other side of the arrow plus something else. So something with calcium in it and that. Well, notice the nitrate is the same on both sides of the arrow. And so instead of breaking it up into a nitrogen and 3 oxygens, I can think of it as a unit, and I say, okay, I've got 2 nitrates on the right-hand side. How can I make 2 on the left? Well, a coefficient of 2 would multiply all of that, and so now I have 2 nitrates on the left. So that's what that means, and that's a nice little shortcut for polyatomic ions, and it's just, it speeds up, offers a better chance of success. Fourth one down. Balance oxygens and hydrogens last whenever possible because they do oftentimes show up in multiple compounds on the left or the right. And so they kind of go back to the second bullet point, just one thing at a time. For odd even numbers, oftentimes we can look for a common multiple. And then lastly, when you are done and you think you are balanced, always do a final tally, whether it's a physically written down tally or if you just kind of count them all up again. Because often you think you're done and then you're not quite done. And this is where I see really a lot of students experience less success because they don't go back and final tally, and then they miss something that they would normally have otherwise caught. Okay, example to balance. So here we have a substance, or a reaction rather, with some substances, ammonium chloride combining with calcium hydroxide. These two substances will react together to produce calcium chloride, ammonia, and water. Now this is not a type of compound, or excuse me, a type of reaction that we would ever be expected to predict in our class because it doesn't fall into our templates. That we'll talk about later on, but it actually, everything here we can write some formulas down for. So let's just go ahead and write this down. So ammonium chloride. So what is ammonium? Ammonium is NH4 with a positive 1 charge. Oops, that does not look like a 1. It looks like an H. Okay, so there we go. Oops, hang on just a second. There we go. With a positive 1 charge. Chloride has a negative 1 charge. They balance, and so NH4Cl plus. Calcium is Ca with a 2 plus charge. Hydroxide is a negative 1 charge. And can't emphasize enough, if you're memorizing these ions, think about how quick this is. And so we got to crisscross these. And so when we do, we end up with calcium hydroxide in that form. Produces calcium chloride. Well, calcium again, 2 positive charge. Chloride is a negative 1. Got to crisscross to make it CaCl2. Now ammonia is just a common name for a substance that is kind of one thing that, had we been in class together, it would be one of the few compounds I would just ask you to memorize the formula and the name. We don't have many, but that's one. Water, of course, is another, but we're so used to water. Most everybody knows it's H2O. Okay, so that's how you can go from a word equation to a chemical equation. Now, there's some symbols missing. I don't have states of matter or anything, but that certainly is the process to do it. I'm not going to balance this one because I have the whole thing balanced in a nutshell on the next slide where it's all typed out and a little bit neater. So let's take a look at that. Okay, stepwise. So what did I do here? One thing I did was I actually, let me change the color of my pen. Maybe it'll stand out a little bit more here. So right here, notice I wrote water HOH, and that's fine for water. It's still H2O, but HOH allows me to see the hydroxide right there, and that hydroxide allows me to more effectively see, oh, hydroxide is on the right and the left, and it's intact, and so I can balance those as a unit, like the whole polyatomic ion thing. Whereas notice ammonia over here, NH4, is not the same as, the ammonium, excuse me, is not the same as ammonia. So I can't balance that as a unit. That's not a polyatomic ion. Well, one of the first things I can do is I could start with a hydroxide, since we're talking about that, and I see 2 hydroxides here, and I only saw 1 here. And so I put a coefficient of 2 out there to multiply. So 2 times 1, I now have 2 hydroxides on the right, and I automatically have 2 hydroxides on the left. So the hydroxides currently balance. Let's move on. So now we're going to look at the chlorines. So I initially have 1 chlorine on the left. Coming over here, I have 2 chlorines on the right. And in order to have 2 on the left, then we would simply need a multiplier 2 times, and that would be our coefficient of 2. Okay, so the chlorines now balance. The hydroxides are unaffected, the chlorines balance. What can we do now? Well, we can now do the nitrogens. So here is nitrogen, and I have 2 because I've already added a coefficient here, so or put a coefficient down, so that's 2 times nitrogen. So when I come over here to the ammonia I only had 1 originally, so I'd have to put a coefficient of 2 out there, so 2. So now the nitrogens balance, and everything else that I have done is unaffected. All right, so where can I go from there? Well, let's check to see oxygens and hydrogens. So coming over to here, so here I have 2 two hydrogens, or 2 times 4 hydrogens rather, and so that's 8 hydrogens. And I would add that to over here on the hydroxides, because I do have to keep track of them all, so I have 2 over here, so plus 2 more hydrogens. That equals 10 hydrogens total on the left. What do I have on the right? Well, let's do a count. Here I have 2 times 3, so that's 6 hydrogens. And I have 2 times 2 here, and I have 2 times 2 here, so actually I have 4 more hydrogens there, which equals 10 hydrogens, and the hydrogens actually balance. Even though I did the hydroxides, the hydrogens still balance. I should check all of that. What about the oxygens? Well, over here on the left, I only have oxygen in the calcium hydroxide, so I have 2 times the 1, so I have 2 oxygens. That's a horrible 2, sorry about that. And over here on the water, I have 2 times the 1, and so that would be 2 oxygens over here. So they actually already balance. So by balancing everything else, I had a good time with the hydrogens. So everything worked there and worked with the oxygens. So notice I almost have done a tally at that moment. And since I was in tally mode, I could say, okay, 2 nitrogens on the left, 2 nitrogens on the right, 2 chlorines on the left, 2 chlorines on the right, 1 calcium on the left, 1 calcium on the right, and then I have officially done my tally. And so I'm good to go. I believe this is balanced, and I've double checked it, and so I'm confident with that. Okay, let's take a look at this one. Description to a formula to a chemical equation. So with aluminum sulfate is going to combine with magnesium hydroxide to form 2 compounds as products. Well, if I want to go from this description to a word equation, I could, but there's no need to because that's just replacing some symbols. I really would like the formula equation because I want to balance that. So what is aluminum sulfate? Okay, well, let's do aluminum, and I'm going to actually change my ink color. I think the yellow stands out better for some things, so I'm going to go to yellow. All right, so let's do aluminum. So aluminum has a 3 positive charge. Sulfate is SO4 with a 2 negative charge. They do not balance, and so I got to crisscross to give me Al2 parentheses SO4 3. Plus, it's going to combine with. Then I have magnesium hydroxide. So magnesium is a 2 positive charge, hydroxide is a negative 1 charge, and they don't balance, and so I got to crisscross to make it Mg parentheses OH2. You know, so with the crisscrossing, with the ions, and with the memorizing of the ions, all of them, see how quick and efficient this could be, so you're not bogged down looking up the ions and looking up the charges, that you can actually get to the heart of the problem, which is to combine them to create a formula to then balance an equation. So again, for efficiency, it's just nice to be able to focus on one problem and not have to be bogged down with so much others. Then we have aluminum hydroxide. So aluminum is still 3 positive and hydroxide is still 1 negative. They got a crisscross here to make it Al parentheses OH3. And magnesium sulfate. So magnesium, 2 positive charge. Sulfate is a 2 negative charge. They actually cancel, and so I can just write it MgSO4. I really don't need parentheses, so I will not write them. Okay, so there we have a formula equation, and I believe all my formulas are correct. Now I could double check to see if it's balanced. So 2 aluminums on the left, 1 aluminum on the right. As soon as I do that, I know this equation is not in balance. Some formula equations actually self-balance, where you write them down with their formulas and they just actually are balanced already. This one is not. So I would have to then go in and actually go through the balancing process, which is just comparing left to right and using coefficients to multiply things in order to get the proper amounts. You can never ever, by the way, for aluminum hydroxide, let me just scoot over here for a minute, for aluminum hydroxide. I can never just break in the middle of a compound and put a coefficient in the middle of a compound. It's just not possible, because that, A, it's not a format, and B, it would interrupt the representation of the compound, and the compound would not actually appear that way in nature, where you could have, you know, like a 2 there, and somehow aluminum hydroxide has 6 hydroxides with 1 aluminum. It never does that. It's always 1 aluminum to 3 hydroxides. So we can never put a coefficient in the middle of a substance just for the convenience of actually balancing that. So just a word there, because every once in a while it does come up, and it's a valid question. Why can't you do it? Okay, I believe this is typed up, so let's do here. Okay, so here we have aluminum sulfate. I've written them all down. I think my formulas are correct. Quick review, let's see. Okay, moving on. Okay, so when I start to balance this, I say, well, let's start with the aluminum. It's the first thing I see. So I'm going to do 2 aluminums on the left. I have 1 aluminum on the right, and so a coefficient of 2 will fix that at this moment. So now I have 2 aluminums on either side. Okay, those are balanced. Where can I go from here? Okay, so I've left my 2 there, and now in this. Now what I see is, hey, let's use the whole sulfate polyatomic ion grouping and say I have 3 of those, right? So I have 3 of those over here. So can I get 3 of those over on the right here? I can, because I can do that. So now I have 3 sulfates on the left and 3 sulfates on the right with this coefficient. Okay, wonderful. Well, now, let's see if everything else is balancing at this moment. Well, actually no, because I have 3 magnesiums, and so over here on the left I only have 1 as written, and so I would have to come over here and also fix that. Well, if I do this, what do I have? Let's do a tally here. So I have 2 aluminums, and I have 2 aluminums. I have 3 sulfurs, and over here I have 3 sulfurs. I'm going to break it up now because I want to make sure everything does balance. I'm going to ignore oxygens for the moment. I have 3 magnesiums, and then over here I have 3 magnesiums. 4 hydrogens, because they only appear once, so 3 times 2 is 6, so 6 hydrogens. 2 times 3 is 6, so 6 hydrogens there. So everything balances. Now I do have to check the oxygens, and they're in multiple spots. So 3 times 4 is 12 oxygens here, plus 2 times 1, which is 2 times 3, so there's 6 oxygens there. So there are 18 oxygens on the left. Over here on the right, I have 2 times 3 oxygens, so that equals 6 oxygens for that compound. And then my coefficient here of 3 times 4 gives me 12 oxygens, and that is 6 plus 12 equals 18, and my oxygens balance. So this whole thing balances, and I've done my tally, so I am good to go. The coefficients in order are 1, 3, 2, 3. And I don't write the 1 down for the aluminum sulfate at the very beginning. It's assumed. You can write it if you want, but those are the coefficients, and those are the coefficients in order. Okay, quick tally. There we have. Okay, sometimes we have odd-even issues. And so sometimes a common multiple will work. So let's check this out. We have barium chloride reactions with aluminum nitrate to form product. Okay, well, let's go ahead and write this down. So barium chloride looks like that because that's a 2 positive and that's a 1 negative charge. You got a crisscross. Reacts with aluminum nitrate. So Al parentheses NO3 2. Why do I know that? Well, that's a 3 positive, and nitrate is a 1 negative, and I got to crisscross that one as well. Well, predicting is in a future presentation, but what I would know is the cations exchange their anions, and so that'll form a barium nitrate product. So that'll be barium nitrate there, 2 positive, 1 negative. And then aluminum chloride, which will be AlCl3, aluminum 3 positive, chlorine 1 negative, crisscross. Well, where does the odd-even issue come from? Well, let's focus on the chlorines, because I can do the bariums, but 1 barium on the left, 1 on the right, so they're actually done. So let's take a look at the chlorine. So here I have chlorines. I have 2 on the left, but over on the right, I have 3. Well, I can't get the 2 up to 3, and you can never take away. You can't get the 3 down to 2. So what can we do? That's where the common multiple comes in. So look for the low common multiple, and of course between 2 and 3, the lowest multiple is 6. So let's make 6 chlorines on both sides by doing 3 times 2, so 6 chlorines, and over on the right-hand side we would do 2 times 3. Now my chlorines are in balance. But of course, I've kind of goofed up the bariums, so let's fix the bariums. 3 bariums now on the left, and I would have to do 3 bariums on the right, just to fix those. Aluminums are goofed up because I initially had 1 and 1 and they worked, but now I have 2 on the right, so I have to come over here and fix my aluminum by doing 2 on the left. Okay, well, I have coefficients on everything. I do not see where I can reduce anything. Notice 3, 2, 3, 2 does not reduce any further. And I would do my tally. 3 bariums on the right, 3 barium, or on the left, 3 bariums on the right. 6 chlorines on the left, 6 chlorines on the right. 2 aluminums on the left, 2 aluminums on the right. And I can just do this really quickly with 2 nitrates because nothing breaks up here. So 2 nitrates on the, or 2 times 3, I'm sorry. Whoa, Spence. Sorry about that. 2 times 3 is 6 nitrates on the left, and 3 times 2 is 6 nitrates on the right. So they all balance, and you could break it up into the nitrogens and oxygens in this case, and it'll still work out. Okay, so there's your odd-even issue. Try for common multiples. Okay, that's just working that out. I'd forgotten I had actually typed this one up. So, okay, here's an interesting situation where it's an odd-even issue, but it's not a common multiple. Now, this comes up less often, but once in a great while, you'll have this even-odd issue, but the reason why is this. So check this out. I have methane, okay, methane, and it's going to combine with oxygen, and it's going to form the 2 gases of carbon dioxide and water. So when I look at this, I have the CH4, and I have the O2 and the CO2 and the water. So I go to balance 1 carbon on the left, 1 carbon on the right, and move that. But check this odd-even issue out for a minute. Notice on the left-hand side I have 2 oxygens, but on the right-hand side I have 2 and 1. I have 3 oxygens. But it's impossible to really do an easy common multiple because the oxygen is spread over 2 substances, not 1, unlike the previous example. So that's an issue. What you can do in this case is, hey, if I've got an odd number like this 2 and 1 broken up, can I just even them up somehow? Could I maybe just, if I say just quickly go with a low coefficient of 2, now I have 2 oxygens here, and then 2 plus 2 is 4, and so now I have an even number on the right, and an even number is much easier to balance right to left. Well, that would be an easy way to do it. So that's what I look for when an odd number presents itself and it's broken up over 2 substances. Well, at this point now, let's go ahead and continue balancing. So now I have 2 oxygens plus 2 oxygens on the right, and so I can come over here and fix that with 2 times 2. Now I have 4 oxygens on the left. 1 carbon still works, and 2 hydrogens molecules, 2 times 2 is 4, and so over here I already have 4, and so that balances. And that is actually my tally, but you could go back through and redo your tally. Okay, so there's another odd-even issue. So these are things that come up. Like the chlorine, the 2 and the 3 in one substance, that comes up a lot more frequently than something like this, but there's a heads up for you. Okay, that's pretty much it for balancing. Balancing is just a lot more trial and error, and I would certainly read the book and do any of the non-graded practice and any of the graded practice as well, only after you're set and ready to go. Let's talk just a couple of slides on energy and reactions. So all physical and chemical change involves energy. This is something we've talked about since chapter 1. I just want to remind you of this, in that with chemical reactions, energy is always involved, and it can be involved one of 2 ways, and we've already talked about this many times. Actually, it's always come up in conversations. So it can be endothermic, where energy must be put into a situation in order for a change to occur. In this case, for chemical reactions, we can treat energy like it's an ingredient. And an ingredient would be what we would call a reactant in a reaction. So if you want to have substance A combining with substance B, we may have to also add energy in order to make this reaction occur to make our products. And so here, energy is more like a reactant, and so you can see that. You could also have a number if you knew the exact amount of energy that should be for A and B. Once in a while, instead of the word energy, you may see a delta above the arrow, which would indicate. Sometimes you could even see a temperature instead, like 15 degrees C, if it's a very specific reaction at a very specific temperature, kind of like cooking. Or we can do an exothermic. And if it's exothermic, energy is like a product. It is produced in the reaction. And so that might be like where C plus D produces some products, and it releases a lot of energy in heat, light, somehow. And so you might see energy written as a product. And here again, it could be a number instead. You're not going to see a symbol like a triangle, like the Greek letter delta or anything at this point. But this could be a number instead, like maybe 400 kilojoules per mole. And that's typical. That's a standard way to show energy for a chemical reaction. Some number kilojoules per mole. Kilojoules is like SI or metric for what we would call calories in the U.S. system. So now every once in a while, or not every once in a while, but many of these exothermic reactions, which are very spontaneous most of the time, do require a little bit of energy to get the whole thing started. So think about a campfire. Campfires, are self-sustaining. As long as you keep feeding it wood, it'll keep burning. But campfires do not start by themselves. You do have to light a match. You do have to light a lighter. You do have to have something, rub a stick together, whatever it's going to be. But you have to provide a little energy in to get it started. And once the reaction is started, that reaction is self-sustaining and releases, in that case, copious amounts of heat and light. And so that amount of energy that you have to put in to get something started is called activation energy. Yeah, that's a term that comes up. Okay, what equations tell us? We're just about 4 slides away from being done here. So, first of all, the significance of an equation. Here up in number 1. Coefficients show relative amounts of reactants and products for an ideal reaction, just, a reaction on paper. The coefficients will tell us the particles that are involved, and they can also represent the numbers of moles of a substance. And so particles, that's how we balance equations. We balance them by the particles. We think 1 atom of this, 2 atoms of that, and we balance. However, that's not useful to practical chemistry on a lab bench. What is useful on a lab bench is moles. Remember, they're just huge numbers, Avogadro's numbers of these substances. And so those are useful to us because those are measurable quantities, and they are visible quantities in most cases that we can use. So a chemical equation here at the bottom, really when we think about balancing, what we're looking at is this. We're looking at the substances, and then we're looking at a molecule and molecules and atoms, and that's how we balance, and that's where the coefficients come from. But notice the coefficients also, same numbers, can actually represent mole amounts. So if you take 1 mole of methane and combine it with 2 moles of oxygen, you will produce 1 mole of carbon dioxide, and you will produce 2 moles of water. That is useful, practical, and measurable in a normal lab situation with typical equipment. So that is a very useful skill set. Now, also, and what is really cool in the lab is this next thing. If you have a balanced equation with coefficients, and we then know, okay, that's also representing moles, 1 mole, 1 mole, 2 moles, 1 mole, and 2 moles respectively. We can also do the mass because we can calculate the mass of 1 mole of methane. That's just a mole to gram conversion. 1 mole of methane has a mass of 16.05 grams. 2 moles of oxygen has a mass of 64 grams because remember it's O2, so it's 16 times 2 to get your O2, and then multiply that whole thing by 2 to get the 64. Here's carbon dioxide. 1 mole of it weighs a little over 44 grams, and 2 moles of water just a slightly bit over 36 grams. And now in the lab, because moles, while we work with moles, we can't measure them on a balance. We measure grams on a balance. And so this is where we then can get into experimental chemistry, where the idea of the mole can come through by doing the masses. And by the way, interesting thing here, because of law of conservation of mass, whatever the total mass is on the left, the mass should equal that on the right. And it does, 80 grams on and 80 grams on. Okay, this slide tells me that pretty much we're at the end of this presentation. That section 2 actually comes up. Remember that section 1 was broken up into 2 parts. So section 2, which is actually a very short conversation, a very short presentation, will actually be section 2. So it'll be part 3, but it'll actually be section 2 out of your textbook. Okay, thank you very much. I'll see you in part 3 of the presentation.